Hi, so in this problem you're asked to show that the derivative of cosine is negative sine, starting with the infinite series, the Taylor series for cosine and sine. So what you can do is look at the series for cosine of x and list the first few terms. You can also do it with the whole sum, but let's just list the first few terms and see what they are, right? So if you plug in, you start at j is 0, you're gonna get 1, and then for j equals 1, you're gonna get negative x squared over 2 factorial. Then you're gonna get plus x to the 4 over 4 factorial, minus x to the 6 over 6 factorial, x to the 8 over 8 factorial, and so on. Okay, so this is the series for cosine. All right. So it's basically all the even powers over the same factorial as the power, and they alternate in sign. Okay. If you list the sine, the series for sine. Right, so again, start with j is 0. These are odd powers over the odd factorials. So for j is 0, you're starting with x over 1 factorial minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial, and so on. Okay? Alright, so let's take the derivative of the cosine term by term. So if I do d dx of cosine of x, the derivative of 1 is 0. Alright, derivative of this is 2x over 2 factorial. Negative, the derivative of this is 4x cubed over 4 factorial. Next is 6x to the 5 over 6 factorial, 8x to the 7 over 7 factorial, and so on. Right? So if you compare these, right, you can see that all the fractions will simplify. Right, so let me have d dx of cosine of x. The 2 cancels, and you get negative x over 1 factorial. With this factorial, you have 4 cancels out of the 4 factorial, so you're going to get x cubed over 3 factorial. 6 cancels out of the 6, right? 6 factorial means 6 times 5 times 4, and so on. So that front 6 cancel, and you get x5 over 5 factorial, and x7 over, this was 8, sorry, the 8 cancel, you get 7 factorial, and so on. Alright? Factor out a negative. So you have x over 1 factorial minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial. Alright, and then you compare it to the sine expansion, and you can see that this is sine. Okay, so d dx of cosine of x is equal to negative sine of x. Okay, so you can show it term by term. All right. Another way is to go directly to the series. Okay, so if I take the derivative of cosine of x, we want to take the derivative of the sum from j is 0 to infinity of negative 1 jx 2j divided by 2j factorial. Alright? Now, because the way the derivative works, okay, if you have a sum of terms, you take the derivative of each term individually, then this d dx can go inside the summation let me just fix this right here. This j is a power. Okay, so this is the sum of j is 0 to infinity of d dx of each of the terms. -1 to the j, x to the 2j over 2j factorial. Alright, so this is the sum from j is 0 to infinity. Right, so let's take the derivative of this term right here. So we can see that the only thing that depends on x is this, x to the 2j. So you're going to get -1 to the j. This is the power rule. You're going to have the 2j come down and x to the 2j minus 1, 2j factorial. All right. So let's cancel things. Okay, so 2 to the j factorial. So let's say j is 0 to infinity, -1 to the j, 2j x to the 2j minus 1 divided by 2j times 2j minus 1 factorial. Okay, so I wrote 2j factorial as 2j times 2j minus 1 factorial. This is a property of factorials. If you have n factorial, this is going to be equal to 2 times n minus 1 factorial. Like if you have 5 factorial, this is 5 times 4 times 3 times 2 times 1. So you can say that you can pull out that first number, 5, and then what's left over is 4 factorial. So that formula works for factorial. So that's what I did here. Okay. So now you cancel these out. And what we have left is j is 0 to infinity, -1 to the j, x to the 2j minus 1, divided by 2j minus 1 factorial. Okay, so now we want to match these with that formula. Okay, so as it is now, it doesn't exactly match. Like if you look at the powers in the factorial, they're not the same. All right. So what you want to do is you want to do an index shift. All right. Basically, we want to shift the index. All right. So notice that when you take the derivative here, it doesn't really start at j is 0 anymore. Okay, because when you take the derivative of this, if you have j is 0, then the first term is 0. Okay, because of that 2j, right? So 2j you plug in, the first term is 0. So it's like it's not part of the sum anymore. Okay, so this really starts at 1. The first term drops out because it was a constant. Okay. So you want to shift the index. You want to say k equals j minus 1. You're gonna call the index something else. Okay. Which means that j equals k plus 1. Right, so we're going to replace all the j's by k's. All right, so at j is 1, then k is going to start at 0 and go to infinity. Then you have -1 to the k plus 1. Then we have x to the 2k plus 1 minus 1. And over 2k plus 1 minus 1 factorial. Alright, so this is k equals 0 to infinity, -1 to the k plus 1, x to the 2k plus 2 minus 1 gives me 2k plus 1. And then here, 2k plus 2 minus 1 gives me 2k plus 1 factorial. All right? Okay, let me erase a bit. All right, so we're almost there. Okay, we can see that we want a negative here. So this is almost sine, not quite. All right, so we're going to pull out a negative 1. Okay, so we have k is 0 to infinity. Negative 1 to the k minus 1 is negative 1 times negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. And then this negative comes out. So negative k goes from 0 to infinity, negative 1 to the k, x to the 2k plus 1, x to the 2k plus 1 over 2k plus 1 factorial. Okay? And if we look at our definitions, you can see that that summation exactly fits what sine is. So that means the derivative of cosine of x is equal to negative of sine of x. Okay, there we go. So I would say this first attempt here, looking at them term by term, this is a good proof. Kind of working with the first few terms in the series. The one where you're applying it to the summation is a more rigorous proof because you're showing that it works for the whole infinite sum and not just for the first two terms. So it kind of depends how rigorous you want the proof to be. All right. All right, let me know if you have any more questions on this.